Hello, my name is Vincent Zhu, and this is my video lab report for Lab 4 microscopic view of DC and RC currents. So the first part of the lab, we just created this very simple circuit which had two batteries with voltage of 1.5 voltage each on, as you can see on the left side, and we had two different resistors, one that was 47 ohms and the other was 100 ohms, and we wanted to just find the current, and I predicted that the current would be 3 over 147 because since the resistors were in parallel, sorry, they were in series, that we knew that they would have the same current. So we added the two resistances up, and then we just divided, and we got 0.02, which is correct, as you can see in the graph. We then replaced one of the ammeters with a voltmeter, and we looked at the current and the voltage. And we looked at the voltage was 3 volts, because obviously this is a series, and because there's only one loop, then we know that the voltage will be 3. And we also know that the current is 0 because this circuit is actually open and that currently nothing can flow because the wires are not connected properly, which is why it's 0. Here I also showed you where I put the voltmeter at different points. As you can see in the first one we got 2 volts and the second one we got 3. The second one we got 3 because it covered, in between it we covered both of the resistors, but in the first one we only covered one of them. So so that we didn't get the full 3 voltage drop yet. And if we took the red arrow, the red pin, and put on the other side, then we would end up with 0.95. So this is the graph of the voltage throughout, and as you can tell, it starts out. So we drew from point C to point H, and at point C to point D, it goes down a little bit, but not a lot. And from E to F, it goes completely down. And we know that's true because of this graph, of these pictures from before, where I just tested the voltage at those points, and we knew how much they would drop. Therefore, we just plugged in those points, and we drew those lines properly. In this one, what we did was we had two different resistors, and we attached a current, an ammeter, in parallel, and we still ended up with the same current as well, which is also 0.06, which is 0.06 here, which is also equal to the 0.06 from the other side. So from our potential difference measurements in part 5 and the current measurement in part 6, we wanted to find the resistance of each of the following circuit elements. So first off, we wanted to find the resistance from the 47 ohm resistor. We did that by dividing 0.959 by 0.02, which is 47.95, and divided 2.04 divided by 0.02 gets you 102.05. And they're very similar to the numbers that we expected, so we know this is correct. We also do know that the wire and ammeter do not have a resistance because, after all, this is a simulation, so we were able to get this perfect. Here you can see the picture of me just charging up the capacitor, and as you can tell in the first picture, at the very beginning, the light bulb is actually very bright, and at the end, it starts diminishing very quickly. At first, the first trial, it took 2.93 seconds to charge and 7.8 seconds to discharge. In the second one, where there was a higher voltage in the beginning, it took 6.1 seconds to charge and 9.7 seconds to discharge. In order to find the voltage, we did ln of V over V of 0 equals negative T over RC. And we knew that at beginning, it started at 9, at V of 0 was 9, and at 2.5 seconds, it was 6. So we got the RC of 6.165, and and later we got a 3.8 seconds, and we plugged it in again, and we also got 5.799. So what if we were doing this live in real life and we used an actual ammeter instead of an ideal simulated ammeter? The difference is that it would not have 0 resistance, because in real life nothing has exactly 0 resistance. And I think that using a real battery to charge a real capacitor with no circuit, I think that would be that would just be quite instantaneous, and it'd be very, very difficult for us to actually measure, because if there's no resistance, then all the charge would instantly move to the capacitor the second that we connect it, and that'd be very difficult for us as humans, obviously, to measure that properly. Thank you.